I'm going to go about the details in a little while, but this is a sort of hands-on presentation. I hope you've seen that on the Meetup page. So if someone, I can see people are with laptops, so you can try and pull the GitHub repo with all the details. By the way, how many of you actually want to follow on their laptops? Can you raise your hands? Okay, a few. All right, that's cool. Okay, so let's start. Before we start, actually, just so that we're done with that, so thanks for the beers go to Virtus Lab. Rafa, our CEO, is pretty open about sponsoring such events, which is a great thing. Okay, so that's the setup. For the people who want to follow up, hopefully you've done that before. If not, you probably have some time to sort of pull that repo. There is a README file in there that you can get some more instructions. Okay, I'm Grzegorz Gawron. I work at Virtus Lab. We have this big data engineering project that we're doing at the moment. This is for a big retailer. There's quite a lot of various machine learning things they do, forecasting, recommendation. There is even location telemetry recently, and we're helping set up machine learning pipelines for them. This location telemetry is a pretty interesting thing because it's essentially seeing or basically looking at the traffic in store, in the shop, and trying to figure out what people or how to help people find things, for instance. So there's quite a few things. Now, okay, so how I'm planning to do this today. First of all, I wanted to look at the problem, so just look at the sales forecasting in general, then the data that we're going to be using for running the models, the tools. There is Jupyter Notebook for analyzing the data. There is some primer on neural networks. By the way, how many of you, can you raise your hands, have trained any of the neural networks? So even one. Oh, excellent, wow. Okay, how many of you have run your trained model in production? Okay. All right, so that's pretty popular, which is very good. So we're going to be using Keras and TensorFlow, about the reasons why in a minute. And there is also an option for scaling the training to GCL Cloud. So the code we're going to be looking at is done especially in the way that helps it run on Google compute platform. And the last thing, once we go through, so this is going to be a bit of theory, looking at the data and understanding the problem. And at the very end, we're actually going to start training the models, changing the parameters, and seeing how it changes. What helps, what doesn't help. I think this is going to be interesting for you. If someone is following on the laptop, I was planning, so essentially what we're going to do, we're going to get to some point in the model development, and there is many more things that you can actually do to improve it. The plan is, or I wouldn't like to call it a contest, but there's going to be a prize for people that actually improve the model the most. We might leave ourselves a couple of days to get those improvements. We'll see when we get to it. Okay, so what is the sales forecasting? It's probably pretty straightforward. So what you have is you have some timeline, so time on the horizontal axis, and sales value, let's say, or sales volume on the vertical axis. The blue blue line is what the sales was really like, and the yellow or orange line here is what the prediction is for that thing. So as we can see here, it's not great. So this this thing here, just as an example, is done by training one of the models that we're going to be seeing today, and this is done on the first, or actually after the second epoch, so the second training stage. So this is like a fresh model, not fully fitted yet, but it shows that, for instance, you know, it's not able really to say that sometimes the sales were 0, sometimes, so it makes quite a lot of errors, right? So we're hopefully going to see that once you produce better models, they'll be able to fit that sales, the real sales graph much better. But this is the problem. So what we want to do, we want to forecast sales. We want to say, okay, train the model, and then say, okay, so how much is going to be this, or how much volume we're going to have tomorrow in the sales. Obviously, the problem, you can rephrase it in how much volume you're going to have tomorrow and a day after tomorrow and next week, sort of thing. But we are going to start really with just predicting 1 day ahead. Okay, the data. So to be pretty neutral, we're just using sort of publicly available data, which is available via Kaggle. This is real store sales data from Rossmann, but it doesn't matter really. So we have 2 files in there. For the ones of you who have a laptop and follow on the presentation, there is 2 files in the data folder. There is train CSV and store CSV. Let's start with store, just to understand the data a little bit. And so we have a store column. I'm just going to be pointing here. We have a store column, which is an ID of a store. We have some store type. There are various types of store. I'm not sure what CA means, but it might mean a big store or a small store. Doesn't matter, I guess, for now. And some other features which describe the store itself. And then what we have train CSV, which really contains the sales that we are interested in. It contains the date, day of week, the store ID. So in the store ID 1, we have 5,263, let's say, dollars of sale. It might be also some sort of a volume. Again, we won't go into details what it is. We just want to predict that. We have, we have some customers. I understand that the customers that visited the store. We have open, whether it was open or not, some promotions available, whether it was a state holiday or not, or whether it was school holiday or not. So essentially, this is the information about what sort of sales we had, and this is what we want to predict. So essentially, if we know all of the information that is available today, we would like to use that information to predict what sales we're going to get at the particular store on a given day. The sales forecasting that we're running, we are developing or building the ML pipeline for currently is actually very similar. I think the model is actually a bit more fine-grained because you might not want just to know what sort of sales you had at a store. You might want to know that per product. So this product, how many sales it's going to have, that product, how many sales it's going to have. So obviously when you're looking at things like if it's, let's say, water, I don't know, in the summer, if it's hot, it's going to be more. It's going to be behaving completely differently to, I don't know, jam or that sort of thing, or bananas. But in this particular case, we don't care about products. We just have store and sales. Okay, so the first thing probably that is worth doing is to try to understand, look inside, what sort of data you are dealing with. For a few reasons, one of them being that you want to check whether the data is sound or reasonable, because pretty often the data might not be too clean and you need to clean it up first of all. Actually here I wanted to switch maybe to the tool that helps, well, I find useful at least for doing that sort of analysis, which is Jupyter Notebook. How many of you have used it, Jupyter Notebook? Okay. Alrighty, so I'll switch. By the way, let's try whether you can hear me without the mic. Is that okay, more or less? Yeah? At the back? Okay, cool. Because it's just going to be much easier to type without the mic in one hand. Okay, so if you follow the thing, we have okay, so this is the repo from GitHub, and there is a notebook folder. You have two things, explore and prediction. Prediction we're going to use a bit later, but now we have this explore thing. For those of you who are not familiar with Jupyter Notebook, essentially the way it works is you have these cells. You can type in code in there and you can execute this. Then the execution results, the output is being put here so that you can see it. Then you have another cell, and again you can run it and the outputs are seen here. And it's pretty nice because, as you can see now, I have not run anything yet. And yet you can see all of the outputs from the previous run that I've done. So essentially it sort of saves down what it has. So it has this ability to save down the results as well. So it's also, one way that it is useful is that when you're looking at the data and then you go switch to developing the model, it's very often useful to just go back and see, okay, what was that, or what was what were those columns, or what sort of ranges I had. And it's very nice to just go back here and you have it all listed. It's like, a nice way of recording this thing. So, okay, just to go through that, what we're doing here, we probably don't need that, some test code here. So we are reading this train CSV, as we've seen on the page. There is some additional parameters here, but don't worry about those. We'll probably get back to those a little bit later. Right, so first thing I do here is just checking what data types. All right, by the way, we use a couple of libraries. One is called Pandas, which is a sort of data frame library, NumPy, more of a number library, and a matplotlib, which will show us some nice graphs plotted very easily, which is very... Oh, sure, yeah, I hope. I'm probably going to miss some of that. Or maybe what I can do. All right, that should be better, yeah? Okay. Right, so, okay, so data types will show me what pandas, so this is what pandas read from CSV, and it tries to figure out what it actually reads. And as we can see, it figured out that store is an integer and so on and so forth. Interesting state holiday, which initially I would have thought would be just an int, whether it is a state holiday or not, is an object. So that's an interesting thing. So essentially this part of looking at the data is pretty good for understanding what we're actually dealing with. Then we can, by just typing, df column 5 is going to show you 5 first records of your data frame, just to see, so we have sorted that per store, some same day, and the values, and again the state holiday, so by first look just looks like it's a 0, 1, but it sounds like it's actually not. Just looking at store, It's a similar thing to what we've seen on the presentation. We're going to come back to those in a minute, but there is also a few additional things that Pandas gives you. So when you have this data frame loaded, you can describe it, and it shows you some statistics about the columns. So you would have, how many, what is the count of the columns, and as you can see, the count is actually the same across all of the columns because it's just the counts of the rows. And it's about, as we can see, we have about 1 million rows in this data set, in this trained data set. We have some percentiles, so it's going to show you, just looking at this, you can see that, okay, this is probably just zeros and ones, which is open or not, promotion, 0 and 1s. There is school holiday, also 0s, 1s. What do we have? We have sales customers, with mean being about, so sales is about, 5,700 on average across all of the points in all of the stores. We have a max of about 40,000 sales. I find it's useful to look at this because it might show you that maybe there is some problem with the data, like, you might have, I don't know, a couple of millions of sales, and it might sound strange to you, and then you might want to have a look at the data and see that maybe there was a mistake. I don't know, someone just inserted more zeros. So it's just useful to have a look at this. Now, we're going to make an assumption. So obviously, I mean, if you want to forecast the models, you might learn from one store to the other, theoretically. But just to simplify things, first of all, we're just going to focus on one store. So we're just going to select one store and just use this data to train the model and use this store's data to predict the sales for that particular store. So we're going to forget about all the other stores for now. So that's what we're doing here. So we are creating another data frame, which is filtered. So we only get the rows that describe store number 1. Here it is. So we are coming to the point where we, with Jupyter Notebook, we can draw some graphs pretty easily. So essentially you just set up a figure. You can give it some parameters like how big it should be. You then run commands that try to plot something. So in this case, we're going to plot a histogram of this DF sales. Remember, this is our store number 1. And here we go. This is where we come to those different types of columns. So what I find useful is divide the columns into the sort of categorical columns and continuous columns. Continuous would be where you have a continuous number. So sales, it is from 0 to whatever we've seen there, 40,000. Whereas day of the week, we know there is only 5 or 7 categories. So there is 1, 2, 3, 4, 5, 6, 7. And we know that, there is certain sequence. So like Tuesday is after Monday, but it might not be that important. It might be more important that on Mondays, I don't know, there's more people buying bread because they ran out on the weekend, for instance. I don't know whether that's the case or not, but it's categorical in terms of, the relationship between 1 and 2 representing Monday and Tuesday is not as relationship with sales, where a sale of 1,000 and 2,000 tells you that, 2,000 is twice as much as 1,000. Whereas in categorical 1, it doesn't give you that relationship. So that's why, I like to put them apart. And this actually helps as well in drawing them. So we can draw some histograms for sales and customers. And again, this is just to get a feel for the data. So we can see now for customers, right? So, we're looking at sales. So there's about 5,000. Just looking at that on average, and as we've seen before, the real average calculated across all the samples was 5,700, probably right. although we are looking also at store number 1, and that's average were on the big data set, so it might be a bit different. But you know, just to understand that, as you can see, there is a big number of the sales where the sales were 0. So I understand there is probably a day that the shops are closed maybe, and they just don't sell on that day. That just gives you some insight. We might not use it now, but you know, later on it might just help you with something. Now for continuous plots, it also makes sense to draw something like box plots to just visualize what my percentiles are for sales here and for customers over there, which, well, the scale is not really the same, so you don't see much from over there. But again, for this particular store, DF sales, as we can see, you know, we have sales at 0 and then going sort of up to 10,000 more or less. But again, nothing unusual. We were looking at some unusual stuff that would tell that we need to do something about the data, like cleaning up that data or not. But it sounds like this data set is not that bad in the end. And one thing to have a look at categories. It's pretty useful to do these value counts. So what it does, it sort of groups by the category and then gives you the count. So we have, maybe it's better to look at open. So we have 172,000 of zeros in the open and 844,000 of ones. Now again, just to check that, and we're going to the state holiday, and this shows you, you know, why it's not 0 and 1, because there is obviously some kinds of holidays. There is, I understand, no holiday, and then there is ABC. So we might also use that in our training to actually figure out, maybe, I don't know what sort of holidays ABCs are in this case, but no, promotion, yeah, well, it is a bit not nicely done, but yeah, it is written down at the end. So that's day of the week, and state holiday actually shows this. There is school holiday, what we think is nice. Okay, so just plotting the sales, just to again get the feel of how it looks like. So yeah, we're going and plotting that, and as you can see, it drops to 0 quite a lot of times and pretty regularly. So that would mean that yes, there is probably some day or a couple of days sometimes that there is no sales. Okay, so we're at the end of this. By the way, just to, because I've run this on a pre-run Jupyter notebook. When you want to run it yourself, you can either run all the cells and run by one by one. When you see the star, that means it's calculating, and when the star is gone, that means it has calculated. So now we have like a fresh copy of this. Okay, so coming back to to our presentation, we leave that thing on, and as you can see, here are just dumps of what we were looking at with the Jupyter notebook. One thing actually with the state holiday, again, there was a problem there that you had a 0 and then you have a string 0, which were treated as two separate things. So this would be an example of a thing that you might want to look at, because if you don't notice that, you might treat them as separate labels, something completely different, whereas probably someone just made a mistake or there was some problem with the data storage that actually read it as string, not a 0. So, you know, that sort of things, this analysis allows you to find things like that. Okay. Right, so now that we've looked at the data and we know the problem a little bit, let's talk a little bit about neural networks. I didn't use the term deep learning because it's too cool, I think. Neural networks sound just fine. Right, we're going to be treating that more or less as a black box because what I want to show is that, you know, it's a nice tool. It's a tool that you can take. If you know what some parameters mean, you can fine-tune them and iteratively get at the good model and better model, and actually get something that works and fits, or sorry, predicts what you want to predict pretty well, actually. But I would encourage you anyhow to you know, have a look at those things like deeper. There's great courses on the net. There is one on Coursera by Andrew Ng, who's a researcher and you know, a guy that popularizes. I'm not sure whether that's a correct word in English, by the way, but the whole idea. Anyhow, so we're treating that as a black box. What we'll have a primer which is going to tell us something about the architecture and what sort of knobs you can turn to change the behavior of the network, which is going to be pretty useful and very nice to experiment with. What this black box means for us is really, it has two ways of accessing that. First, you do a fit, which trains the network, so you give it some data, and you give give it, so for instance, you would say something, okay, here is my past 2 weeks of sales, tell me, so past 2 weeks of sales, and now the next day after those 2 weeks, the sales were, you know, that number. So we sort of teach it, we give it, okay, if you see those 2 weeks of sales, then the next number for sales should be this. And we sort of run through all of the data like that. And this is what, pretty clumsily, I try to put it like MN, so that you have this big array of M samples with N features. And then you give it also the result that it should try to fit into, so the real sales on that day. So it's just one number in our case. And then you have a second method, you have a predict, where you give it just a row of features, so essentially a state of the data as of today, and ask it, okay, now you give me what is the prediction of the sales tomorrow. So that's the thing. Okay, so we're going to go through these neural networks. We're going to probably be talking a little bit about this data processing and a sort of approach that I find is pretty useful at training the models. Okay, I'm not sure whether you've seen that. This is a playground TensorFlow org, and it's pretty cool, and I chose this to actually show you. Am I connected to? No, I'm not connected to the internet, but I will be in a minute, I guess. Just a second. Okay, or maybe we're just gonna go through that statically. But yeah, if you have your laptops, it's very good to have a look at there, because you can. So essentially, this is your neural network online, and you can train it, and you can see how it behaves after a while. So it's pretty cool. When I connect to the internet later on, I will show you on the screen as well. But what we wanted to go through now is just the architecture of the thing, so that we know what we're talking about. So neural network is essentially, you have these units, calculation units. They are divided into layers. So there is input layer, or it's called features here. There is a first hidden layer, as it's called, second hidden layer, and a third hidden layer. And then there is the output. And what happens is that you feed it the data that you have here, and you give it, when you want to train your neural network, you give it the expected output. So in this case, this is a problem with classifying points in this square, and the classification should be the blue points. The model should say, so if you give it coordinate like 0, 0, it should say, oh, it's blue. If you give it coordinate -6, -5, it should say it is yellow. So essentially you want to train it to recognize this figure. And you train it by feeding it all of these points that you can see here. So you take a point and you know it's blue, so you say, okay, this point, coordinate x1, x2, and then at the end you say, and this is, and it should be blue, right? And then you take the yellow one, and so on and so forth. And essentially what you do, you run through all those points in the training set, and you feed it to the network, and the network adjusts those units inside so that after a while it is able to actually fit it like this one here. So the background here is what the network was trained to do. So essentially it fitted it pretty well in this case. Yeah, but that's the thing. So you have layers, you have units, and the way you're thinking about the architecture of your network would be, you would think about how many layers you want to put it, how many units you want to put in there. You would be thinking about what sort of features you want to put, because as you can see, there is some x squared, x1 times x2, so you might have various combinations of those features. In our case, the features will be whether the store is open or not, whether there is a holiday or not, what were the last 2 weeks of sales. So we're going to put it like unit by unit. In each unit there is going to be a sale for a given day. So that would be the way we're going to do it. Obviously there is various approaches, and I'm just going to go for sort of simplest approach first of all. Yeah, and maybe just a note that this is a basic architecture of neural network. There is various kinds of networks. There is recurrent networks that essentially try to keep state so they are used, maybe a good example is with generating sentences or understanding sentences. So essentially when you say some sentence, there might be some context that you're talking about, I don't know, you're talking about Krakow, and then you're mentioning later on that in this city there is something like that. So it needs to remember that we're talking about Krakow now and not about some other town. So these recurrent networks are designed to do this, like keep this state from the past. And initially I was thinking for this case, you know, I'm just going to start with that because it sounds like, okay, we need to remember what happened before, we need to have a context. But in the end, I just went for this simple thing. And during the test, you can actually train one and train the other and see what difference it makes. I didn't find, to be honest, with the way I was doing this, too much use of using more complex architecture. And I think a good way is to just start with a simple one. Okay, so we have layers, we have units. Obviously, they're connected to one another, but that does not matter too much. There is one more thing that they show here. Here's you have this graph, which shows you a loss. And this is a keyword that essentially tells you how many errors the model made. So there is some sort of metrics. It's calculated in one sort of problems this way, another sort of problems that way. But important thing is to understand loss is a bad thing, so you want to minimize it. And as you can see, as we were going, okay, so here's the time on that. Again, horizontal axis is time, and we feed more and more data into the network over time, and it tries to adjust the weights. And as we can see, initially this loss was high, and then over time it sort of dropped down. So the network was able to adjust its weights, so it was correctly identifying, you know, the points, classifying the points that you wanted. And this is pretty, like, sort of important thing, and we're going to get to that a bit later as well. Okay, and I think I talked about everything. One more thing. As you can see, it sort of goes over time as you feed it the data, but it is not just one set of data. So So you have a set of data, but you feed it once, it adjusts the weights a little bit, and then you take the same set of data and feed it again. And you can do it again and again, and like feeding one big set of data is called one epoch. And we're going to get to that a bit later, but it's very important how many epochs you're able to feed into your network, because over time you hope it's going to improve. Okay. Just having a look. Yeah, okay. Now, so there is quite a lot of knobs that you can turn in the network. So the question is, you know, how you should go about it. Should you do it in random? Probably what you could do as well, you could imagine you have some, I don't know, they're called hyperparameters, by the way. So you might have 10 of them, or I don't know, 100 of them. More likely, I guess, 10. So if you have 10 of them, each of them can be in some value. You could do a sort of grid search where you say, okay, the first parameter can take one of 10 values, the second parameter can take one of 10 values, and then you sort of multiply this. You have this grid of points that you want to check out, and you run all of those trainings, and then for each of them, you check which model is best. You could do that. It takes quite a lot of processing power, and with the bigger models, I guess it's not very feasible. So another way of looking at this is to get a guide, and one of the guides is this bias and variance thing. And I think it's pretty, maybe not very intuitive, but pretty important to know. So what we're looking at here is a graph. This is a loss graph that we've talked about. So essentially, the lower the better. If we got to 0, that means it was able to really hit and predict everything, classify everything correctly. In here, we see that, you know, it has some error. So looking just at the green line and looking at the timeline here, at the horizontal axis, you see the epochs, how many epochs of data we were able to feed through the network. So essentially we, at the very end, there were 200 times the same data set was fed through the network. So we had 200 times. Okay, so the green line here essentially is what was your error or your loss on this training set. So essentially, you have your network, you run the training set, you tell it what you expect at the end, and it doesn't hit it, right? So it does something wrong. So you say, okay, there is a little bit of loss for me, right? And you do it again and again and again, and this is your loss painted in a green line. So you are not able to fit with your network your training sets. And this is one important thing because it gives you a guide of what to do next. But we're going to get to that later. And the yellow line, this is a very important concept because what you need to do is it would be easy to just take all of your data, train your model on this, and say, okay, I have a great model. But this is really not how it works because you take that model and you run through it, the data that it has not seen yet, and then, you know, you have completely no guarantee how it's going to behave. It might just not work at all. So it works perfectly on your training data, but then when you actually run it, it sees some new pattern and it just doesn't work. It just doesn't hit it. So this is exactly the thing. The yellow line is once you've trained your model, you take the data that your model has not seen yet, and you ask it to predict that data, and you see what loss you get. So essentially what we see here is that green line had a lower loss than the yellow line, which is expected, right? Because it was trained on a certain piece of data, so after a while it sort of adjusts to it and get used to that and is able to do it. And then it's fed the data that it has not seen yet. It's a little bit different, so it makes more errors, essentially. But why is it important? Because that allows you to do it step by step, in a way. And I'm going to do your training step by step. So there is, I mentioned this Andrew Ng. He has this sort of recipe for how you could do it. And when you look at this bias, so bias is this training set error. When you have a high bias, that means there is a big error on your training set. What does it mean? It means that you're not able even to fit your network to the training data that it sees, right? So, which is not really good. How is it going to behave on the data that it has never seen yet? So this is high bias, and there are certain things that you can do to deal with this high bias. You can give it a bigger network, which is supposed to be more powerful. You can train it a bit more. You can use better optimization algorithms. We're going to be talking about those in a little while as well. You can use some different architecture, as I mentioned, about LSTM and the normal standard neural network. On the other hand, with high variance, what it means is that, okay, well, you fitted your training set in some way. You might have a bigger or a loss or a lower loss, but then you compare your set, your validation, there's various names for this. I'm going to call it development set. So the set of test data that your model has not seen yet, you run it and you see what error you get. And if that error is much, much bigger than your training set, you have a high variance problem that essentially it's not generalizing too well. So you fitted your model to the data that it can see, but then when you run it in real data in live, it is not able to do it well, right? It is just fitted too well to that training set and is not able to generalize. And again, when you see this is the problem, then you can go through some other steps. So you can get some more data. We're going to go through what dropout and regularization means as well. And you can also deal with that through architecture search. But so essentially, this is your guide, right? So, so just to summarize that, when you see that this area here, so this distance here, so your loss is high, and you would expect that maybe I can do better, then you can do one sort of thing, try to make your model more powerful in a way, just to summarize that. When you see later on that you've done that and you pushed it as far as you could, then you try to make this yellow line go sort of closer by, because the yellow line is really what you're after. You want to train the model to just deal with everything it can see, not just with the data that it has seen once, right? You want it to generalize. So first of all, you try to minimize this distance, then you try to minimize that distance. So just to, summarize that. I know it's quite a lot of theory, first of all, but I think it's worth going through that before we actually start doing something that moves. Okay, so just to see a little bit how it worked. So you have epoch number 1, which is this, and epoch number 61 here. It starts with 0, so essentially it's after the second epoch and after the 60-second epoch. And as you can see, it looks pretty nice the way it sort of tries to fit things. So in the first one, it wasn't able to deal with the 0 sales. In the second one, almost always it hits it. Not always, but it is better, right? Also with those things, yeah. So it looks nice. Yeah, you sort of see how it learns, and it's pretty cool. I like that. And another thing is here. So this shows you an average absolute error. So essentially, if the sales were 3,000 and you said it's going to be 2,700, the error is going to be 300. And on the other round as well is going to be 300. So this is this absolute error, and as you can see, it's sort of squeezed. So it was the second epoch. It was like this, and look at the scale as well. This starts with minus 3,000, and this with minus 6,000. So we can see that it sort of gets better over time. just as an illustration. And that's another illustration for this actually. So we have the first epoch, how those absolute errors behave, and then you run through all the epochs up to epoch number 97, and sort of gets smaller and smaller. It's still not perfect, but yeah, it's getting better. And as you can see, also this time around is actually different. This is a little bit random because of the tool of the coloring. It doesn't really improve over time, yeah, it's a bit random. So after a while, it is not able to do it, in this particular case. Right, okay, so now the tools. So we have Keras. Keras is a Python library that allows you to nicely specify the model in a very easy way. So essentially we were looking at those layers. So the only thing you need to do to define a layer in Keras is just add to the model a layer of a certain type. Dense would be a basic layer which is connected to everything else. Then you give it some parameters. Don't worry about this for now. Then you add another layer, which also has 8 units. This one has 8 units. And then you add a layer at the very end with 1 unit, because we just want one number in this case. We just want to have the sales number, and that's it, for 1 day. Then you compile the model. You give it how it should calculate this error for the whole set for you. Mean squared error is essentially, it sort of goes by sample, checks what the error was, and then squares it and takes the mean or average out of this. And it's pretty good because when you had a big error, it's going to be squared, so it's going to be multiplied, and it's going to matter much more than a smaller error. That's why it's mean squared. So it's quite often used. You have an optimizer, so how many of you heard about gradient descent? Yeah, excellent. And about Adam? Okay, it's just another way of optimizing. It's also very interesting how those things are, what the algos behind those are. Pretty cool. So it's Adam, but we can play with that later, so that's not a problem. And then you put what additional metrics you want to have apart from this loss, so the mean squared error. And in this particular case, I gave MAE, which is this mean absolute error, so that because it gives you this feeling for how wrong you are with your model. So it's how much on average, what is your error on average. So for instance, if the sales are about 3,000 and you have on average 300, that is like 10% of error that you're making on average. Okay, so this is how you define the model in Keras. So again, just add layer by layer with some parameters, compile it with, again, some parameters about how it's run. Then you run this fit on your data. X is the inputs, Y is the expected outputs. How many epochs, how many runs through the data it should do. There is some callbacks. We're going to look at the code a bit later, so we might have a look at what that is. And once you've fitted that model, this forecast model has all the weights adjusted to your problem, so to this X and Y that you gave it. And now what you do, you say, okay, now predict some different X. And hopefully this is the X that the model has not seen yet, the line at the above. You predict it, and you have Y hat. It's just, there is this little hat above Y, which is like sort of predicted stuff. Right, so you get that Y hat, and then you can, again, calculate what error you got for the test set, if you know what was expected and what you actually got out of the model. For the data it has not seen yet, you can compare it, you can run your statistics on this as well. Or you can actually use it in production as a forecast. Okay, yeah, I know there is quite a lot of this, but that's probably the last one we need to go through just to have our running smooth. So TensorBoard. So this is pretty a nice tool because it allows you to draw those graphs automatically. Those graphs here. So essentially what you have runs of your model here, Obviously, this is coded up, how they should be named, and so on and so forth. But you have those runs, and as you can see, we can draw these training loss curve and the evaluation or test loss curve. And we can be guided by this as to what to do, or try to squeeze it to the bottom as much as we can. All right, some example here. So here was some initial model that wasn't doing that great, right? And then we got better with this model, and then we got even better with that model. So that's how it would work. So we probably start with something simple that is going to have high loss, high error, and we're going to go down. Okay, so we're going to skip that for a while. So this is running the stuff on the cloud. We might get to that later, but I just want to get into doing something so that it is less talking for me. Okay, right, so let's go to the code. Okay, so we have, so this is this code for from the GitHub repo. By the way, so, sorry.
Can you increase the font for the screen size?
Sure.
Thank
you. We might not need that much of this. Okay, so for those of you with laptops, are you able to run any of those things? So essentially, the way we're going to be running this, there is this run next script, which will essentially just get the next run number and will run our model, and that's it. I don't want to, maybe let's start actually running some training first of all, just so that we can see something moving, and we might get back to going through the code maybe if you're going to find that useful. Right, so you have this thing, and if you run it, it's going to train your model. So what happens here, you see epoch 1 out of 50 because it was configured to run 50 epochs, so 50 runs of the data. Then it's a second one, and it shows you what loss it had. Our MAE, mean absolute error, and it's sort of, you know, it starts with 0.20, it goes down, 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 probably to some number 0.09, and that does the best thing. And now if we go to TensorBoard, by the way, this is a thing that you start with the command that you also have on this GitHub README file. So there is Python TensorFlow board, and then you give it the logging directory. And then it's going to go there and figure out what you've ran, and it's going to try and show you things. Okay, so we have it running. You will have your address URL here. Right, so if we now go, okay, we didn't have that, but luckily all of that is running locally. Okay, so it figured out that we ran thing number 2. So if we now look at those guys, we're going to see some graphs. Just asking the guys who are using the laptops. Are you running those things as we speak, or is it working for you? More or less?
More or less.
Less or more? Okay. All right, so we're just going to be going here, but yeah, do shout if you have some questions. So, okay, so there were some runs before, and you can switch them off. So this is the last run that we've run, because it goes like number by number. There was zeros, ones, and twos. What we have here is we have our training set loss, and we have our development set loss, which is the yellow bit. And again, this is the thing we were talking about, that This one is the loss, the error that you got on the training set, the data set that you were training your model with, and this is the set that your model has seen for the first time. And it was able to do like not that bad, I guess, but still worse than the training set. Okay, so we have some values, right? How to interpret those? Again, we were talking about this mean absolute error that can be nicely interpreted as this error that you get like 3,000 sales, but you set 2,700, so it's 300 error. We have the 0, 1, 0, 1, 8, so it's not the same thing. Why? Because we scaled the model to the values between 0 and 1. So if the highest sale was 7,000, now it's going to be 1. And everything else is sort of squeezed. And the reason I did it that way is because the network adjusts the weights much better if you feed it that data. So we can understand it as more or less 10% of the absolute error we have. So if we were thinking about 5,000 on average sales, so we'd have sort of 500 error. But it's not that important. I mean, all we want to do, we want to get a better model, better at predicting stuff. As we go along, we're going to try to get this line lower and lower to be better and better. Okay, so we've run the model. Okay, let's try to run it again just to see that we're going to have a new one. I'm actually going to increase maybe the, where do we have, so that, no, this is not run. Oh no, it's here. Yeah, in this run next, you actually define how many, so I'm just going to put it as 200, and maybe then you also specify how many times you want to evaluate your model with the data it has never seen yet. So this is the development set. So I'm not going to do it as often. Just every 50 epochs, it's going to evaluate that. Still going to be enough to draw our thing. Okay, so it's running again, and it's going to be running a bit longer now. We can go into this thing here, refresh that, and as we can see, we have number 3 now. And again, as you can see, it follows exactly the same path. And it's also pretty interesting because there is some randomness inside there, but it's following exactly the same path. It's because the seed for the pseudo-random numbers is set at the very beginning so that you can have it repeatable, so that if nothing changes, you really see no change here. Okay, so it was able to calculate things up to 200 epoch. The first one was up to 50 epochs, so it's sort of, but we can see it does not improve too much when you give it more epochs, yeah? So it's not great. Okay, so just following on in our presentation, so this is the thing. One more thing that we can do, we can actually now draw the predictions we got from our model, from the, again, the development set, the one that the model has never seen yet. And you can do that using this, this other notebook that we have, the prediction notebook. There is some functions in there, and again, we can go through that. I'm just aware that that it might be a bit boring for you. Maybe we're going to have a break a little bit and then go through some details. But what you can do, what this code does, it goes through all of the predictions that you've made during your run, and it draws you those predictions here. So what we've seen, so this is after epoch 4 and this is after epoch 44. Actually, I think probably it would be useful to actually have that. So if we have a list of predictions, oops. I'm just going to try to make it draw the first prediction and the last one rather than the ones in the middle, just so that we can see it in an extreme way. Oh, I forgot the bracket. And we're just gonna so we're gonna take just 2 of those. So we're gonna take 0 and maybe the one at the very end. Okay, and I'm just gonna try and run the whole lot. Okay, drew 2 of them, and as you can see, actually I selected the run number 0. Which one was I supposed to select? Let's have a look. So that was number 3, the one that we ran. So I'm just gonna change it to 3 and run it again. It generated it. Okay, so we have, whoops. What am I doing wrong? Was there only one prediction in there? Oh no, I know. There is this step thing here that tells you whether you should omit some of those along the way. Yeah, and we have the first prediction which was made after the epoch number 50, and the second one which was made after epoch 200. So it's still quite a lot of epochs it went through before it actually evaluated it. So we can see it's already was able to fit to the data. And yeah, when we look at the differences, there is no, it doesn't sound like it's really much better in the second one, right? Just going back here, 50 was here and 200 was here. So this difference, it didn't improve that much really. So I guess that's expected, yeah, that it wasn't too good. Okay, so now we know that we can run stuff, we can see it drawn, we can see the loss, and we know how to optimize it. We want to just get those graphs down, and we're going to get better predictions. And we can also draw the predictions to visually just see what's happening. Right, okay, so we've added more epochs to it, and more or less that's what you see, that it sort of went a little bit further, but didn't improve it too much. Now, what if we add more units to our model? So now, you know, if you've come with a laptop and it works for you, you can just play for yourself as well and just see whether you can make it work. So we have this model thing that, right, we can try and give it more units in the neural network. So we just give it unit 8, and we're going to try it running now, and we'll see what sort of difference it's going to make or not. And we should be seeing some next run. I'm just going to leave the last run so that it's easier to compare. Okay, so adding additional ones didn't really help much, right? We are more or less on the same thing. We can, okay, we can do various things, but I guess I'm going to try and do it the way it is done in the presentation. So we're going to add another layer. So we're going to try to make it even more powerful, this thing. Input shape is required to be only on the first layer because it defines how many features we're going to pass it straight away. We're going to go again for the details of that maybe a bit later after a little break. But for now, let's run a couple of more of those and see where we're going. So the thing where it stops to evaluate stuff, to load up the evaluation data, the development set, and evaluate it, save down the results. So that's why it's sort of jagged a little bit. Okay. I'm gonna refresh so that we see all of the new stuff. Okay. So again, there's not much difference, to be honest. And I guess this is what I've seen as well, as you can see from those things when I was running that before. Now, let's add some data to it. So essentially, so where we started was with a very basic model. So we started So here is a thing that defines what features we take into account. So we take into account sales. So this is the data that we feed and say, okay, based on this data, you should try to predict this tomorrow's sales. So we gave it sales, and the look back is how many days back we give it. So we give it 20 days of sales, of past sales, and we ask it to predict tomorrow's sales. So this is the only thing we did. We don't look at any, whether the store was opened, whether there was a holiday or not. So we don't look at that. And, you know, so what happens if we actually add a column that, you know, gives you some more details, right? So if we add this open thing, and again, this is where I find this explore thing useful, is that you can see at what data you have. So you have nice 1-0 open data, so we can just add it straight away. And we run it again, just with that thing on. Okay, and let's see what's happening. All right, so it sounds like it does it much better. It's not much surprise to me because I've done this before. But it's always nice, you know, like, so if I disable that so that you see, it was able to do much better on the set of data that it has not seen yet than the previous model on the set of data that it was trained with, right? So it's pretty cool. Yeah, it should be much better in terms of how it fits the stuff. Okay, so let's just go through some more examples. What do we have? Actually, I might add them one by one, but as you can see, like if you added day of the week, not much change. If you added promotions, you know, a little bit better. School holidays, not too much. And this is a summary. So I'm just gonna add them one by one here. So did we have, so what did we have there? We have a promo, we had school holidays. What else did we have in our school holiday? I'm not gonna add the state holiday yet because it's not a nice sort of number value, because when you have a value like this, you actually have to convert that straight away. So you have to treat it as labels, then sort of take those labels. So not doing that yet, very simple model. So what can we take? We can take promo, open, and we can take day of the week as well. And by the way, I guess I made a mistake here. It's a holiday, not holidays. And we're going to take day of the week. Okay. We're going to run this on all of those guys. Okay, and if we go to our tensor board, I'm just going to leave the last one. So yeah, there is some improvement. Not amazing, but there is some, which means, you know, it was able to actually use that data usefully somehow. Now, okay, there is some parameters that you can tweak as well. So far we were giving it more data to consider. What if we actually try changing the model? So we have this activation function, which, yeah, there is a lot of stuff to talk about, so probably we're not going to go too much into detail. But, so this is this sort of non-linear parameter that you give to every unit, so that it doesn't pass it linearly, but it sort of maps it into some function. And the sort of function you map it is defined here. So there's various functions. If we start with relu, which is one of the popular functions, let's see what sort of difference it's going to make. So we're going to make it on those two. We're not, oh sorry, not on the dense layer. This is the one I didn't want to make it on. Why? Because we don't want to map the last layer to anything, because mapping really means relu well, some other guys are going to be mapping from the full set of data from like minus whatever millions to plus millions into, for instance, 0, 1 or minus 1, 1, so that it's better to use it also for the network. But you don't want to do that on the last unit that you have, because this is the unit that is supposed to show you the sales. So the sales can be 4,000 or 5,000. It's not sort of scaled. So yeah, so you have this relu activation, and I'm just gonna do it on this one as well. And let's run again. And let's have a look at the TensorBoard, what effect it's gonna have. Oh, something problem. All right, I did a bad job of doing this, obviously, not that bracket, because it's inside the layer rather than the add function. Once again, we should start seeing something now. Yep. Okay, yeah, so relu sounds like it works a little bit better, although not a great amount better. Well, it starts being better a little bit later on. So that's a little bit better. Let's try something else. There's another one which is tanh. Okay. And we're gonna see how that works. I'm just gonna check what, all right, so the Adam optimizer, and we're just gonna show, okay, cool. And we're sort of getting to the little break, maybe. So don't worry, I know there was quite a lot of ground to cover. Okay, so this is the last one that we have. Oh, this is not the last one that we have. Okay, so these two. So we have the yellow line. Sounds like it's actually worse, right? So it went up. So this is not what we want to do. So the previous run was better. So actually, probably relu just works better in this case. Okay, yes, so you can also play with optimizers, whatever. So, okay, and maybe just to highlight that this is where the cloud computing comes in pretty handy, because this is a very iterative process. I don't think, you know, it depends on the problem, on your data, what sort of configuration works best, and you're going to get the best model out of it. So it is useful sometimes to just try many different combinations. And if you can say, you know, I have this big cloud and can just run lots of stuff on there, then you can train multiple models at the same time, and that in the end just choose the one that works best. So, so yeah, but just so that you have a feeling for this. And this is why this is written in a way that it's easy to use from Google Cloud Platform, where they have TensorFlow and can run exactly the same thing on there. So when I connect to the internet, we might actually see that in action as well. Okay. So that's that. Maybe I'm just gonna run this for few more. Well, let's give it like 2000, and maybe let's run that for 500 more. Okay. And in the meantime, we can just see, you know, those little steps that we were doing. I'm just going to make it a bit. Yeah, those little steps. So you go step by step, and in the end, you're just getting your model better and better. Hopefully, at least. By the way, so we can now just take one of the latest models. So model number, which one was better? So that was, okay, 09. So we can take 09 and try to draw this prediction that we had here. for this one. And let's see, so this is after 49 and this is after 199 epoch. So what do we see? Right, so this actually got a bit worse here, but I guess some of those are getting better. So it's not like you got a perfect fit with that model, but you did get a little bit better. I think when we're gonna get this model that runs longer, so number 10, let's try and show this. Well, that sounds like it went over the roof here. Is that good enough? Or is that for 1000? So it doesn't sound like it's improving a lot over time, but let's have a look at tensor boards. Oh yes, we can see this line that shows you this untrained data is actually getting worse. So we could actually see that on the thing, right? So that sounds like this is a worse fit than this one here. Just looking, you know, visually on this. Okay, yeah, not getting much better. Okay, so I think, right, so let's talk about extensions, and we're going to have a little break. We can continue later on for those of you who want to get into details maybe of the code, but I just don't want this to be too dry because there's quite a lot of talking and you're not talking anything, so I guess it might be a bit boring after a while. But just the last thing I wanted to go through is, you know, what sort of, because this is a very simple model, what sort of things we miss. Obviously what we miss quite a, you've seen that we got the big jumps from adding more to the data. So the information that the store is planned to be opened or closed is a very important information to predict how many sales you're going to have, right? So if you don't include that information, you're missing out. So adding that information is pretty important, and we have those, for instance, the state holidays that we have not included because they were labeled. So there is this label encoder that allows you to encode it into numbers, and then you can take it as a feature, and you can do that, so that would be one thing to do. One hot, you maybe have heard about this, so this is about this categorical features. When you have a feature exactly, let's say these are those 4 types of holiday, 0, 1, 2, 3. And you don't want to encode them as one feature because then the model might think, okay, the holiday number 3 is somehow 3 times more than holiday number 1. Whereas there is no relationship between the number at all. So what you want to do, you want to sort of encode it into 0 ones for the 4 holidays. So holiday 1, either it is holiday 1 or it's not holiday 1. Holiday 2, is it holiday 2 or not? So this is one hot encoding, and you could do that to help it. We haven't talked about a third subset of data that usually you would put aside. So we divided our test data set into 2 parts, the training data and the test data, the development data. Usually once you optimize for this development set over a while, so you tune parameters over a while, you're going to get better and better and try to fit better and better in that development set. But then, okay, your model hasn't seen that data, but you have seen that data and you have tuned it to hit that data. So you want to have yet another set that the model hasn't seen yet and you haven't seen yet. And this is going to be a test of how it's going to behave in real life on the data it has not seen yet. And this is this third set. And this is useful for seeing how good your tested or maybe your model is also compared to other models. So that would be another thing to do. The thing I mentioned at the very beginning, we might want to learn across the stores. So maybe the patterns are similar across the stores and we're not using that information at all. We just filter the information from one store and that's it. Obviously, you can try some different architectures. There's recurrent networks, for instance, and see whether that is going to give you something or not. So these are just some of the things you might want to do. Okay, so there's some references. And before we go on the break, I wanted to invite you for this data conference we are setting up in April next year. There is going to be some, I'm going to put on DataKrk, there's going to be some discounts for you guys if you want to.